Okay, what I want to do is finish up measurable sets by answering rather, the four following questions. The first one I mentioned this earlier. Does the outer measure of a set C being 0 mean that it's countable? Two, if we have, let's say, a continuous function from R to R, just a regular Calc 1 continuous function, then is the inverse image of a measurable set measurable? So we know that the inverse image of a Borel set is Borel, but the question is the inverse image of a measurable set also measurable? You can ask the same question for f in 2. Is the direct image measurable if E is measurable? And fourth, you could ask, is the set of all Borel sets equal to the set of all Lebesgue measurable sets? Well, the answer for all of these is no. So we're going to focus on answering the first one. Actually, the answers to 2, 3, and 4, coming up with counterexamples, really all depend on the construction of a set C where the measure is 0, but it's uncountable. So we're going to do this right now. And so here, we're going to construct a counterexample called Canter Set. Okay. So here, for time reasons, we're not going to really get into this. This is proposition 21. Actually, both of these are in Royden, in the Royden's book. And last but not least, the answer here is no because of proposition 22. And in fact, somewhat interestingly, here proposition 22 says that there exists a subset of the Cantor set that is not Borel. Okay. So how do we know this is measurable? Well, if A is a subset of a set of measure 0, then A has measure 0, and hence A is measurable. So there exists a set of measure 0 that's not Borel. Okay. Again, here, this is the Cantor set. So really, and for proposition 21, you actually use the existence of a non-measurable set in conjunction with a function cooked up using the Cantor set. So really, the Cantor set plays a big role in all of these. So it's rather special when it's rather special if 2 and 3 are true. And so one kind of interesting thing is that for homework, we'll prove, or you'll prove, that 2 is true for Lipschitz continuous functions. And remember what that means. It means there exists some big M where f of x minus f of y is less than or equal to m absolute value of x minus y for any x and y. And this m is independent of x and y. Okay. And as we'll see in that problem, the key is that such functions map sets of measure 0 to sets of measure 0. Okay. All right, so let's talk about the Cantor set. And I'm not sure if there's particularly a very good, three, not two. 3 is going to be shown to be true for Lipschitz continuous functions. I don't know if there's a very good sufficient condition for 2 to be true, but I'll look that up. All right, so what I want to do now is describe the Canter set. Okay. Okay, so we're going to define a sequence of nested sets, subsets of 0 to 1, as follows. So we start off with 0 to 1. We get the C0, C1, C2, or C1, C2, et cetera, as follows. So how do I get capital C1? Well, I'm going to remove the middle third of 0 to 1 to get C1. Okay. So when I remove the open middle third of 0 to 1, I get 2 closed intervals. So let me draw a picture here. Really can't properly describe the Cantor set without a picture here. So, so here's C0. All right, so, so I remove the middle third. And what's the open middle third? Well, it's just 1/3 to 2/3. I'm breaking 0 to 1 up into 3 pieces. 0 to 1/3, 1/3 to 2/3, 2/3 to 3/3, which is 1. So I move this here, and I'm left with 2 intervals, 2 disjoint closed intervals, each of which has length 1/3. Okay, and I kind of just repeat this process here. So let's describe C2. And yeah, so I should say C1 is the union of these 2 disjoint closed intervals. So C2, how do I get C2? Remove the open middle third from each interval in C1 to get C2. So C2 is going to be the union of these 4 disjoint closed intervals by removing the open middle third from 0 to 1/3. So I break up 0 to 1/3. as 0 to 1/9. I remove 1/9, 2/9, then it's 2/9 to 3/9, which is just 1/3. Okay, do the same thing. For 2/3 to 1/3. I take 2/3, maybe make this a little nicer looking, doesn't matter at all, graphical sake, but it's better. Okay, so 2/3 is, that's just 6/9, so this is 6/9, 7/9. 7/9 to 8/9 is removed. It's 8/9 to 1. So, this each interval in C2 is 1/3 the length of each interval in C1. Each interval in C1 has length 1/3, so each interval in C2 has length 1/9, and there's 4 of them. Okay. There's twice as many intervals in C2 as there are in C1. All right, so continue. So in general, to get Cn plus 1, given Cn, well, this tells you basically how to do it. Remove the open middle third. From each interval in Cn, and take the union of all these disjoint closed intervals to get C, sorry, I meant to get C2 here. Right. And I'll just do one more graphically. I won't write down what the endpoints are. So you just remove the middle third from 0 to 1/9, right? The remaining 2 closed disjoint intervals. And keep doing this for each of the 4 intervals here. And just keep going. Okay. So something to note, just by an easy induction, because at each, given C0, we break C0 up into these 2 intervals, keep them. We break each interval in C1 into 2 more intervals and keep them. Remove the middle third and keep the remaining 2 intervals in each interval in C1, et cetera, et cetera. So at each stage, we get twice the number of intervals from the previous stage. Well, we start off with 1 interval, so by an easy induction, Cn is the disjoint union of 2 to the n closed intervals. So C1 has 2 intervals, C2 has 4, C3 has 8 intervals. And each interval in any stage has length 1/3 of each interval in the previous stage. Okay? So the length of each interval is constant at each stage, rather, and the length of each of these intervals at any stage is 1/3 the length of any of the intervals in the previous stage. Well, we start off with length 1, So each interval in the first stage is 1/3, then it becomes 1/9, then it becomes 1/27. So it's 1/3 to the 0, 1/3 to the 1, 1/3 to the 2, etc., etc. So so each has length 1/3 to the n. Okay. So by countable additivity, clearly this says that the measure is, well, you have 2 to the n disjoint intervals of length 1/3 to the n, so it's just 2/3 to the n. So let's say big C, the Canter set, is the intersection of all these CNs. I mean, we could start at 0, doesn't really matter. Yeah, certainly these are nested. That's pretty clear because, well, at each stage, we're taking the intervals from the previous stage and removing the middle third of each of these intervals. So, we don't add anything new, we just take away. So these are certainly nested. Okay? And so certainly there's stuff in this Cantor set, in the intersection. Any of the endpoints of any of the intervals, you can kind of graphically notice that that's going to remain. Like 0 is never removed. 2/9, if you imagine just continuing this, that's never removed. Any of the endpoints of the intervals at any stage is never removed. Well, that only gives you countable number of elements in C. Okay. So I'm going to prove in a moment that C is actually uncountable. So first, let's get the measure of C. So this is closed. It's the intersection of closed sets. So it's certainly measurable. So by continuity of measure, you should definitely be able to get what the measure of C is. It's going to be the limit of the measure of Cn, then goes to infinity, and that is simply 0. All right, so let me prove the following little proposition. That is C is uncountable. And again, this is what's called the Canter set. What's interesting, and we'll do in a moment, is that you can do this kind of procedure and remove not quite 1/3, but remove, let's say, the middle alpha/3 for some alpha between 0 and 1. If you do that, you actually get a set called a fat Cantor set. It's called a fat Cantor set because it has positive measure, which is quite interesting. Get to that in a moment. Okay. All right, what's the proof of that? Assume otherwise, so that assumes C can be written as this countable list of numbers in 0 to 1. Okay. So I want to use the nested interval theorem to get a contradiction to this. So I'm going to use it, do it in the following way. Okay. So little c1 is not in one of the intervals of big C1. I think that's pretty obvious. Big C1 comprises of two disjoint intervals. So first of all, little c1 is in big C, and certainly big C is a subset of big C1. Big C is the intersection of all the big C's. Big C is a subset of big C1. Little c1 is therefore in big C1. Big C1 is the union of these two disjoint intervals. So little c is not in, at least, well, it's in one of them and it's not in one of them. Let's say f1 is one of the disjoint intervals of C1 that little c1 is not in. So let me draw a picture. So let's say, I don't know, little c1 is in this closed interval of big C1. Well, let's just say f1 is the other one. Okay, right. Okay, so in some way we're going to continue on. So little c2 is in big C, is a subset of big C2. Same logic as before. This we can guarantee is not in one of the subintervals. Let me put it this way. It's not in one of the two disjoint intervals of C2 contained in F2. Okay. So what do I mean by that? And let's, sorry, F1. Call it F2. Okay. So what do I mean by that? Well, C2 is in big C2, so it could be in any of these four intervals. Let's say it's in this one. Okay. Well, then, if that's the case, if C2 is in this one, then I want to pick one of the subintervals of F1 that's a part of big C2 where C2 is not in it. So I would just say this is F2. Now, if C2 was, say, instead here, so kind of get rid of this here, then I can pick F2 to be any one of these. I just want a subset F2 of F1 that is in big C2 where little c2 is not in big F2. Okay? That's all I need. So if C2 is here, pick F2 to be either one of these. If C2 is here, pick F2 to be either one of these. On the other hand, if C2 is here, pick F2 to be this one. If C2 is here, then I would pick F2 to be this one. Okay. So, yeah, so it's important to note that F1 is a subset of C1. F2 is a subset of maybe I'll just make a note here. So this is contained in C2. Okay. Yeah, so we basically just continue on. Do one more. Little c2 is not, do c3 rather. This is not in one of the two disjoint intervals of C3 contained in F2. Okay, I'll draw a picture or update the picture in a second. You really should get the idea of what I'm doing. Call it F3. Okay. So again, C3 is a subset of big C. Big C is a subset of big C3. So little c3 is in big C3. All right, so let's say this is where little c3 is. If this is true, then I can pick F3 to be either of these. If I pick F3 to be either of these, then I will have big F3 is a subset of big C3, and big F3 is a subset of big F2. And that's the same thing if C3 is in really any of these 6 intervals. Any one of these two, or these two. I can pick F3 basically to be either one of these, and I'm okay. Little c3 will not be in big F3, and big F3 is in C3, and it's a subset of, big F3 is a subset of big C3, and big F3 will be a subset of big F2. The only time we have to be a little judicious if C3 rather is in one of these. Again, if it is in one of these, you just pick F3 to be the other one. That's all you do. C3 is here, then pick F3 to be the other one, the one interval of C3 that's a subset of F2 not containing little c3. Right. Yeah, so just note, just like before, that F3 is a subset of big C3, and F3 is a subset of F2. All right. So continue on to get, and you can carefully prove that you can always construct these, these Fs by an easy induction. But yeah, these are definitely nested by construction. Each one of these is a subset of CK. Little ck is not in big CK. Right? Okay, so obviously none of these are empty, they're closed intervals. So by the nested, let me call it NIT, the nested interval theorem, the intersection of all these Fs is non-empty because they are a nested, non-empty, closed sets. Right. So yeah, that's the interval theorem says this is not empty. Okay. Well, so this is certainly a subset of the intersection of n equals 1 to infinity of Cn, because, well, sorry, this is K. Why is that? Well, Fk is a subset of Ck, so that's kind of trivial. And this is big C. So this little c is in big C. Okay. So this means that little c is little c K0 for some K0 and n. Okay. So what does that mean? That means little ck0 is c, well, is in this intersection. Well, the intersection is obviously a subset of any one of these individual intervals, particularly Fk0. Well, that's impossible. Okay. So the point is that C cannot be so C is not in this list here. So that proves that big C is uncountable. We just proved that given any list of elements in big C, we can construct a little c, a real number between 0 and 1, that's not in that list. So this has to be uncountable. Okay, so let me describe this kind of fat Cantor set, so to speak, right? And this actually, right, this is, I'll leave part of this as a homework problem, but, so this is basically number 39, make it a little bigger. Let's make it 200%. Okay, so I'll try to make it 250. Not quite. All right, that's a lot better. Okay, so let's say they call it F, I call it big C. Let's say, yeah, you do exactly the same as in the Cantor set, except in the nth stage, you delete an interval of length alpha alpha 3 to the minus n, or each of the intervals removed has length alpha 3 to the minus n, alpha times 3 to the minus n. So what we've done is we took each interval in the n minus 1 stage and removed the middle third. So each of the interval removed, we took, to get to the n plus 1 stage, we took each interval in big Cn and we removed the middle third. So we removed an interval of length 3 to the minus n to get intervals of length 3 to the minus n minus 1. Right? So let's instead just remove intervals of length alpha 3 to the minus n. So if this is a little unclear what we're doing, that's okay. I'll draw a picture. Right. Right, so let me call it maybe C alpha. Okay. So we want to show that this, if we do the same thing but modify it in this way, we get something with measure 1 minus alpha. And the key to doing that is really just continuity of measure, really. Okay, so maybe C alpha is not the best. I'll just call it C also. Okay, so yeah, let's look at C0 here. So what are we doing? Okay, so I still start off with 0 to 1. And this is sometimes asked as a prelim problem, construct this kind of fat Cantor set. It's called fat because in some sense the Cantor set is really skinny. It has measure 0. This has non-zero measure, 1 minus alpha for each alpha between 0 and 1. Okay, so yeah, let me move this up a bit. Okay, so for C1, start off with 0 to 1, nothing special here. So I'm still removing a chunk to get 2 more intervals, but I'm removing, normally I would have removed the middle third. I'm removing something that has length 1/3, or alpha over 3 rather. I'll do it in red, I guess. And just to remind you, alpha is between 0 and 1. So, right, so we're still getting 2 intervals of the same length. Let's figure out what that length is. That's pretty easy. Let's call it L1. Okay, so I'll probably do it here. Yeah, how do we get the length of L1? Well, really not much to it. You take L1 plus alpha over 3 plus L1, you get the length of the previous one, which is just 1. So 2L1 plus alpha over 3 is 1. So L1 is 1/2 1 minus alpha over 3. So it's not difficult, but it gets quite a bit more interesting than just the Cantor set. It's not trivial at all what the length of each interval is at each stage. Let's do one more. Do C2. And you really have to a little carefully do this inductively. I mean, otherwise their head's going to spin. So let's say each one of these has length L2. Okay, so remember the problem says we're removing from each interval of the nth stage an interval of length alpha 3 to the minus n. So this is going to be alpha 3 to the minus 2. So this is going to be alpha over 3 squared. So very easy logic tells us what the length of L2 is in terms of L1. Okay. Well, it's basically L2 plus alpha over 9 plus L2 has to equal L1. So 2L2 plus alpha over 3 squared equals equals L1. So that implies that L2 is going to equal 1/2 1 minus L1 minus alpha over 3 squared. So you can probably already see the induction. I mean, this here really is, L0, really. If you want to say, you want to call this L0 equals 1. Yeah, you can kind of see how the induction goes. So in general, by induction, what has to be true? I mean, I can even just draw a picture here. So the picture is just as follows. So not beautifully drawn, doesn't matter. Let me at least make these the same length. It bothers me if they're not. That's close enough. All right, so let's say this has length. So here we're doing the big C end stage. Of course, there's 2 to the n of these intervals, but let's just look at one of them. That's all we need. So so we were given that this has length alpha and of course big Cn plus 1 consists of 2 to the n plus 1 intervals. Right, so this is what we're given, that each interval, at the n plus 1 stage, we're taking the interval above it, containing it from the end stage and removing the middle interval of length alpha over 3 to the n plus 1. That's what the problem tells you. So yeah, you have to have 2ln plus 1 plus alpha over 3 to the n plus 1 equals ln. So LN plus 1 is going to be equal to 1/2 ln plus 1 minus ln. Check that. Yeah, so it's L, right, that, just divide by 2 and subtract alpha over 3 to the n plus 1. All right, so I claim that, in fact, 2 to the n, L to the n, and this is what I would previously give, what I used to give for homework. I guess that's maybe a bit much for homework. So the claim is that the length of each interval in big Cn, or really the measure of big Cn, is given by the following. Big Cn has 2 to the n intervals of length Ln. So this is kind of trivially the measure of Cn. 2 to the n, L to the n. And it's just easier to get the induction in terms of 2 to the n, L to the n. Right. So it's going to be 2 over 3 to the k. So k equals 1, n equals 1. So really we're actually interested particularly here in 2L1. So what's 2L1? 2L1 is 1 minus alpha over 3. That's pretty trivially, let's write it like this in case there's any doubts. It's not true. This is true. 2 to the 1 is 2. Right, and there's really no sum here. N equals 1 is 0. So, or really there is a sum, it's just k equals 0. All right, so it's true n equals 1. Assume it's true for n, okay? Okay, so, right, so let's go back a second. So 2ln plus 1 is going to be 2 times ln plus 1. It's ln minus alpha over 3 to the n plus 1. Okay. So 2ln plus 1 is ln minus alpha over 3 to the n plus 1. And so as I mentioned, this has been put on in the past on the prelim, so it's really good to understand this construction, really be able to duplicate it. Right, so what do we have? We have it's easiest to work with really the left-hand side plugging in n plus 1. Well, do kind of a trivial thing here. This is 2 to the n. Two times ln plus 1. So this here is going to be ln minus alpha over 3n plus 1. I should mention on like a prelim, you really wouldn't have to prove this by induction. This is pretty clear by construction. I mean, it's really, I guess you're not even really proving it by induction. You're inductively constructing each interval in big Cn plus 1 just by this way. So just by construction, this is really true. So I would say, yeah, maybe induction. I mean, you're inductively defining intervals in Cn plus big Cn plus 1. So maybe construction is a little better. But yeah, you would definitely, I mean, yeah. Okay, so now let's use our inductive step. So this is going to be 2 to the n. What was ln? Well, sorry. So let's distribute the 2 to the n. So this is going to be 2 to the n alpha over 3n plus 1. Okay, so this is, what did we say this was? 1 minus alpha over 3, k equals 0 to n minus 1. This is just, again, my inductive hypothesis. For n. 2 over 3 to the k. Minus, well, let's just factor out a alpha over 3. So that becomes, well, not so subtly, 2 over 3 to the n. And not so subtly, we can write this as 1 minus alpha over 3, k equals 0 to n, 2 over 3, no, it's not n, it is n, sorry, it is n, because this is the last term here, to the n. Okay, so that takes care of the claim. Okay. Okay, so, right, let's see be this intersection here. Right. So again, these are, these are nested closed intervals. Okay. So C is certainly measurable. So the continuity of measure. Actually, I think after this I'll find out. I forget when. I thought this was asked on a prelim that's on the website. I'll double check that. Okay, so yeah, this, like I said, this is definitely more interesting than just the Cantor set. But still, it's not super. So just literally let n go to infinity. It's 1 minus alpha over 3, sum k, k equals 0 to infinity, 2 over 3 to the k. And everything just turns out nicely. 1 over 1 minus, what is it, 2 over 3. This is going to be alpha, distribute to 3. Well, that's 1. So it's 1 minus alpha. Okay. So, right, so that takes care of at least part of number 39. I'm going to give this other part, well, it's closed because it's the intersection of closed sets. And again, I call this C, the book calls this F. I don't know why F, but I guess F is as good as a name for something as, well, not as good as C because C for Cantor. But anyway, yeah, you'll have this dense part for homework. But this at least proves that the measure is 1 minus alpha. Okay? Okay, so I want to finally talk a little bit about how to maybe do this problem a little more efficiently on a prelim. So as I put in a text overlay, these fat Cantor sets do appear on prelims. And in particular, this is June 2015. And this problem here is number 4, right here, is construct a closed subset of 0 to 1 with measure 2/3 such that 0, 1 take away E is dense. Okay, so this is basically exactly what we've done. So remember, for these fat Cantor sets, I'll use the book's notation F, or maybe I'll use my notation C rather. So for each alpha between 0 and 1, we constructed basically this set E here, I called it C, with measure 1 minus alpha. Remember, for homework, you're proving that 0, take away 1, 0, 1 take away the set here is dense. That's homework. Right, so this here, if you have alpha equals 1/3, sorry about that, dump in 1/3, probably the simplest alpha you can really, maybe alpha is 1/2 is a little simpler, but anyway. So this is obviously 2/3, right? So that's where this 2/3 comes from. Sorry about that. Yeah, so that's where this 2/3 comes from. It's just exactly what we've done with alpha being 1/3. Okay, so yeah. So on a prelim, just really guessing or you know, figuring out exactly, you could basically figure out explicitly what the measure of each stage is, which is 2 to the n times the length of each of the 2 to the n intervals in the nth stage. And yeah, I mean, let me do that real quickly. I mean, I told you what it is, but I didn't really tell you how I guessed it. So from before, certainly on a prelim, you should be able to get that 2ln plus 1. Remember, this is the length of each interval, each individual interval, or I didn't really call it stage, but in just literally in what I called Cn for this alpha fat Cantor set. Yeah. And so we just drew a picture, and we got pretty straightforwardly that 2ln plus 1. Really, we got ln plus 1 is going to be 1/2 ln minus alpha over 3 to the n plus 1. All right, but I want, so just kind of reminder, put on the side here. Obviously, this is going to be 2 to the n ln. Each interval in Cn has length ln, and there's 2 to the n of them, so it's kind of self-explanatory. I mean, I've explained, you know, it's just a finite additivity, like I've explained a few times. All right, so let's multiply both sides by 2 to the n plus 1, and we basically got this before. So this is going to be multiply both sides by 2 to the n plus 1. It's 2 to the n ln minus 2 to the n alpha over 3n plus 1. So let's call this, just to make my life a little easier, let's call this xn plus 1, and this is xn. We really want to get what xn is. Okay, so, right, just to rewrite this, xn plus 1 is xn minus 2 to the n. Let me make this a little neater. 2 over 3 to the n alpha over 3. Is that right? Yes, it is. Okay, so this is kind of a pain because you cannot do what you did in 511. You can't just say, well, certainly this is decreasing. This is a decreasing. You can prove that it's bounded below by 0. So the limit exists, and you can pass to, you can just take limits on both sides, but the problem there is if x is the limit, so let's say x is the limit of xn, which I just outlined exists. Well, you take limits here, you're going to get x equals x. This goes to 0. And that's not incorrect. That's nothing wrong with that. It doesn't really help me a whole hell of a lot to say x equals x. So yeah, this is one of those times where the 511 trick doesn't really work all too well. And what I would do is just write down a few of these. Maybe just to get the ball rolling, x0, let's say, remember we defined C0 as just 0 to 1. So there's only one interval of length 1, so this is just 1. It's basically, yeah, xn is 2 to the n ln, so it's just L0, x0. x0 is L0. Maybe make that a little clearer. So I would write down maybe 3 of these if you're doing a prelim, and that'll tell you basically what the pattern is. And you know, if you have time, great, prove it by induction. If you don't, it's not a big deal. I'll probably be grading the prelims, so when I say it won't be a big deal, certainly at least in June, it won't be a big deal. All right, so we have x0 is 1. I don't want to write that down. So plug in n equals 0 here. x1 is 1 minus 2 over 3. Yeah, so it's n equals 0 here. 2 over 3 alpha. So 2 over 3 to the 0 alpha over 3. So this is just going to be alpha over 3. Right. So I would say the key to doing prelims well is not memorizing every proof, but just remembering tricks how to do proofs efficiently. And this is, to me, the trick to do this efficiently. Get it to this point here. So that you can get it to this point here. Ultimately, you want the measure of, ultimately you want 2 to the n ln, so that you can get this very easy recursion and write a few of them out, and and you can, we'll see that the guess I put up, which we proved by induction, is pretty easy to make, as we'll see when I do 2 more. So let's do n equals 1. So this is going to be x1 minus 2 over 3 to the 1. alpha over 3. And let me actually, to make the guess a lot easier, let me leave it as 2 over 3 to the 0. Okay, so this is going to be equal to, let me do it on the next, well, I don't have it written down, so let me move this over a bit. Sorry about these little time wasters. So sorry, it's x1 minus 2 over 3 alpha over 3. Okay, so this was 1 minus, and you can already see the pattern here. It's exactly what we've written down before. I'll do one more, in case it's not absolutely clear. So n equals 2 here. With n equals 2, this is going to be x2 minus 2 over 3 squared alpha over 3. So this is going to be equal to 1 minus 2 over 3 to the 0 alpha over 3, 2 over 3 to the 1, 2 over 3 squared alpha over 3. Make sure that's right. Yeah. Right. I really hope I spelled that right. Anyway, it's early in the morning, so yeah, so your educated guess is that xn at this point should be, it's exactly what I wrote down before. 1 minus alpha over 3, just pull out the alpha over 3 here, sum k equals 0. Well, I have a 3 here, this is a 2, so k equals 0 to n minus 1. 2 over 3 to the k. Right. Okay. So again, really just n equals 1 here. It might be enough to kind of remind you of what this is. N equals 2, 0, 1, 2 is certainly enough to see the pattern. Yeah, and from here, just do exactly what I did before. So, on a prelim, this is kind of the trick I would try and brand in the back of my brain, that you get this kind of recursion here, write a few of them out. You can very easily figure out what your educated guess is for your xn. If you have time, prove it. But, if you don't have time, it's not a big deal. It's really not an issue. Yeah, so just from here, like we did before, this is going to be 1 minus alpha. Okay, yeah, hopefully that was useful on this prelim example. And yeah, all right, next up is measurable functions. And we'll probably realistically end around there. I don't know if I even want to start Lebesgue integration, but certainly, if you understand everything I'm doing, and you understand Lebesgue measurable functions well, doing the Lebesgue integral is not going to be that difficult. And everything on it is up on my YouTube channel, so feel free to look at that if you want to learn it. All right, so long, take care, bye-bye.